Good morning, everybody. So I'm Raffaele Federico. It was a pleasure for me during this year to uh, coordinate the activity of work package 3, where all these partners did an excellent job. And I'm going to give a short overview of what we did in terms of RIS modeling, design, and characterization. So really, in a nutshell, what we want to do is to provide an electromagnetic RIS model and the system level abstraction, design, prototype, characterize the RIS and the control logic for the proof of concept, which is of course very important, and characterize the model, the recent power, the reconfigurable radio channel. So regarding the first point, well, we had a different model that were proposed. One of these is an end-to-end impedance model that is valid for design meta surface, but not about general RIS surface RIS, and was validated on practical design and mapped on to system level communication. This model, which is based on impedance formalism, was extended also to multiple scattering. Also, we had proposed some hybrid analytical numerical model of RIS communication channel and the RIS itself for both transmitting and reflecting wave, and other model that were proposed represented the RIS as a reference circuit and was validated on practical design. And also in the framework of this project, there were some, let's say, specific tool for the simulation of RIS by implementing.
Raffaele,
yes.
sorry, are you changing slides?
No, I'm.
Okay.
Yeah.
Just to confirm.
Yeah.
Sorry for interruption. Please go ahead.
Yeah. So just a short overview on the first part, which was, let's say, the end impedance model that was firstly proposed by our partners, Gabriele Gadone and Marco Di Renzo. In the beginning, it was a very simple model that was thought for dipole models, dipole elements. And so also the RIS is represented as small dipoles. And what we wanted to have, it's really end-to-end model for this RIS channel, where what we wanted to mainly characterize is the active impedance model, the active impedance, and then we can play on this impedance here matrix to have whatever we want. So we compare this with an extension based on scattering matrix. And what is important is that we extend that to some realistic design. This one, for example, provided from CA, which is quite different from the ideal dipole-like representation of the unit cell of the RIS, because actually we don't have just one port, but two ports where two pin diodes. And here we realize that the 1 bit phase shift, which is basically a phase shift between the two states of 180 degrees. And so we had a let's say bunch of simulation and simulation campaign. What we wanted to stress is that the model, the end-to-end model for just a unit cell or more unit cell fits quite well in terms of phase shift with respect to the ideal, the perfect full wave simulation. And so, yeah, this was an example of, let's say, one unit cell that was considered in the project. But what is interesting in the project that we had to develop and the design of very different technologies for RIS with different technology readiness level from different frequency band from UHF up to the D band. And so we invested the pin diode technology, RF switch, MEMS, varactor, and in the higher band, we also have some very specific.
Sorry for interrupting you.
Yeah.
I guess you're showing not the right screen, because actually we only see the same first slide. If you're changing slides,
You don't see nothing.
We just see the first slide with actually not the presentation mode either. So maybe there's a problem there somewhere.
Yes, there's indeed a problem. So I've been talking for a moment.
There was actually the question of George before, but
yeah. Can you see some slide moving or not now?
No, we don't.
Oh.
Now, yes, now it's moving. Yeah, but there's no presentation mode. I just let you know. You should share probably the la fenêtre, and not just the file. Probably this way.
Yeah,
the screen.
yeah, that's let me show it like this, and I really apologize for this. Can you see now?
Now it's in full screen and it's moving. Now it's perfect. Okay, that's
Oh,
perfect. In that way.
wow. It's repeated. Don't let tell me
No, don't
if
repeat. Go ahead. Go ahead.
yeah, was just a slide. Sorry about the models, and yeah, the overview of the model, and yes, and that's I was talking about this. So let's start again from this hardware prototype and the fact that we develop different partners develop different RIS technologies on based on pin diode, RF switch, MEMS, varactor. And what is interesting that we well, we address a very large span of frequency from UHF up to the D band, where in D band also we investigated some B-SIMOS process and for unit cell design. So just to give some short overview on some of them, this was one unit cell that was designed from Guinea wave in the K band. So basically it works that there is a patch, and then while we have some parasitic resonator connected to the diode. So changing the value of the diode, basically we are going to change the electrical length, which results actually into a phase shift. So this is what realize the phase shift that we want to have. And then this unit cell were put together in a huge unit cell composed of 4 panels, each one of 20 by 20. So at the end, it was 40 by 40 RIS, and well, this RIS is also been used in experiments and proof of concept. George presented before the concept of transmitting a reflective RIS. So we have the practical implementation of this with CA, which is basically a RIS that provide a 2-bit phase quantization in transmission and 1-bit phase quantization in reflection. And basically we have, let's say, a multi-layer unit cell with different diodes, and according to the configuration, well, we can make it work in reflecting wave with the 1-bit phase shift. So basically we have the shift of 180 degrees, or in the transmitting mode, we have 2 bits, so which means that we have 4 state of phase. And that's an example of measurement that was done in an echo chamber to show really how it steers the RIS. Another very interesting concept was also proposed by NEC, which is based on RFI switch to the connected different legs. What is also very interesting of this on this design is that you don't only control the phase, but you can also, let's say, switch off some of the RIS of the unit cell and have a reconfigurable, let's say, size of the unit cell. And then this was also measured in an echo chamber, showing indeed the steering behavior that we want to have with this kind of RIS. Another technology was proposed by Orange, which is based on varactor. So the interest of this kind of design is that we have a very well discussed, almost continuous phase shift, so which allow to have let's say more degree of freedom, and and of course we can do some different beamforming. You can see here with this reflecting RIS, and this was also employed in a nice proof of concept that was done in indoor environment by Orange. Okay, so now for the last part is about the RIS radio environment sounding modeling. So we developed some model that are extension of the end-to-end impedance model, and we have just a ray tracing one model that was also implemented. What is also important that we performed the measurement, and just an example here of the measurement that we did is probably is the first measurement that employ both the transmitting rays acting at the base station, different reflecting rays, and the UE that is in different position in indoor environment. And what we shown here is that, of course, in a such rich scattering environment, the reflecting rays related path is one among the others. So we really needed to have an investigation on how the multipath are distributed. But what is interesting is that we proved that this, let's say, reconfiguration of the channel happens in distance and in angle and amplitude as we would like to have. And then, we'll skip this slide because I'm out of time. I would just want to say that the scattering model, the impedance model was extended to this kind of rich scattering environment by representing the scatter as a bunch of dipoles. And so by knowing this channel and knowing also modeling the multi-parameter, while it was proven, and will be shown later in another presentation, that this could be helpful to really optimize the communication. And what we did, of course, it's not only provide the framework, but use also our measurement to prove that this model is valid. And so this is a work that is going to be presented in UCAB, what we show how the directed path and the reflected path by the RIS are very well in line in the model with respect to the measured one. Okay, so I'm going to close here. I apologize for the problem with the slides at the beginning. What is important is that we evaluated the different RIS technology performance. By the way, beside the definition of the band of interest that was explained before, also there are some lookup tables that can be used. We have RIS and electromagnetic channel model that were validated on practical design and several prototypes that were used to as a demo and in measurement. So if you want to have more information and more details on this kind of work, then these are the 4 deliverables of the work package that are available for reading, and you will find much more details on that. And of course, you can contact me or the person that were involved in this work. Thanks all.